This is problem number 3. In this problem, everything is same as given in problem number 2 except heat exchanger is fitted and thermal ratio is equal to 0.75. So what we have to do is that I will actually focus on the in the preceding numericals. I will actually focus on all the new things. So the things are actually the same. Here is compressor, here is high pressure turbine, here is output, here is low pressure turbine generator, and here is a thermal ratio. And the thermal ratio will be between this is heat exchanger that will cause the thermal ratio, that is 0.75. So the diagram will actually apparently it will be as same as the previous one and there will be no change in it. And T2S the same formula, same calculations. Isentropic efficiency the same formula and same calculations. And work input of compressor is equal to gross output of high pressure turbine into 0.98. The same, all the things are same, but here we have written T5 because now T4 is equal to T5. And isentropic efficiency of high pressure turbine is equal to N high pressure turbine is equal to T4 minus T5 divided by T4 minus T5S. So isentropic efficiency of high pressure turbine is equal to 0.83 is equal to 923 minus 761.57, 923 minus T5S. So T5S is equal to 728.49 Kelvin. The things are same, all the things are same. So T2 minus T1, and here we have T4 minus T5, and T4 is and now the output of the combustor. T5 is unknown, and we will use this relation to find the value of T5. So the basic thing is that we have to use our mind to calculate what is given, for what is given and what we have to calculate. So we will develop a relation in our mind, and these miracles will be very easy. And isentropic efficiency of high pressure turbine is equal to T4 minus T5 divided by T4 minus T5S is equal to 728.49 Kelvin. So simple. Now we will at the same line P5 by P4. It is the pressure ratio of the high pressure turbine is equal to, by this formula, compression. This is compression ratio, and this is formula from the basic knowledge of thermodynamic 1. And here it is P5 is equal to 1.57. Similarly, T6 by T5 is P6 by P5 into gamma minus 1 over gamma. And T6 we will calculate as we know that T1 as we know that T6 is equal to T6 1.57 and the same T5 that we know. We have calculated T5 here, and we will use this T5 to calculate T6. We will use this T5 that we have calculated above to calculate the value of T6. Actually, I am preceding this numerical at very fast because I will actually focus on the new concepts, and if you want to learn this numerical, you should go to the first video in which I have explained each step in very detailed manner, and in the all the next videos the approach is that focus on the new thing and just pass all the previously described things. So T6S is equal to 682.10 Kelvin. Simple. Now isentropic efficiency of low pressure turbine is equal to N low pressure turbine is equal to T5 minus T6 divided by T5 minus T6s is equal to 0.85 is equal to 761.57 minus T6 divided by 761.57 minus 682.10, and T6 comes to be 694.02 Kelvin, and this is T6. Now thermal ratio. Now this is the basic point that we should know. Thermal ratio is T3 by T2. Why and how? So I will go to the basic diagram. T6 it is a T3 by T2 and T6 by T2. Why? So this is T6 that is coming toward the heat exchanger T6, and this is T2, and this is output, and this is again input. So this heat exchanger is what it is actually adding heat in the process 2 to 3 in order to decrease the uh, combustor work. I mean the combustor power input that is being generated by the combustor. And T6 and T1, T6 and T2, this is actually the ratio between this is actually T6, that is the exit of the low pressure turbine. We have actually taken all the work and now we are going to use this heat in this process between 2 to 3. So let's come here. So T6 minus T2, T6 minus T2. T6 output of the low pressure turbine, temperature at the output of low pressure turbine, that is that we know. T2 we already know, that is the output of compressor. T3 output of the T3, that we do not know. Now the basic thing is that from the previous numericals we actually from the previous numericals, if I draw here, this is process 1 to 2, this is process 2 to 3, this is process 3 to 4, and 4 to 5, 5 to 6, and then again here 1, 2, 3, 4, 5, and 6. From the previous numerical we know all the things. We know T2, T1, T4, T5, T6. The thing that we do not know this T3. So in order to calculate this T3, what we will do, we will use this concept of thermal ratio. So thermal ratio is T3 minus T2 and T6 minus T2. The output of low pressure turbine minus the output of compressor uh, divided by in denominator, and in the numerator we have the output of the heat exchanger divided by output of compressor. So we will use this concept to actually solve it. Thermal ratio is equal to T3 minus T2 and divided by T6 minus T2. We will plug in all the values and we will get the value of T3. Now net work output is equal to 76.18 kilojoule per kg, and heat supplied is equal to 325.13 kilojoule per kg. And we know that cycle efficiency is equal to net work output divided by heat supplied. Net work output divided by heat supplied. We know net work output, and we know we actually want to know the heat supplied, that we also know. So the cycle, we will calculate the cycle efficiency. All the other steps are same, So the basic fundamental difference I have already cleared, that is the concept of thermal ratio and how to use it. So heat supplied, now where we have used T3, we have used T3 in the heat supplied, that is CPG T4 minus T3. Until unless we do not know T3, we cannot know the heat supplied, and so we cannot use it here. So it is basic uh, demand of question with the heat exchanger to know the temperature at point 3 to calculate this heat supplied, and then use this heat supplies to calculate the cycle efficiency. So this is the concept, and we know that net work output is T5 minus T6, that we already know. So one new thing is added in this question, that is actually the thermal ratio, and I have given you the concept that how to deal with it. Stop.